Okay. So for ER diagrams, they're made of entities and relationships. These entities should be thought of as sets. And the relationship is going to be either a one-to-one relationship, a one-to-many relationship, or a many-to-many relationship. Now, when you have two sets, if they're one-to-one, that defines both of them. But if they're one-to-many, you could have one set be one-to-many. You could have a set A have a one-to-many relationship with set B. At the same time, set B could have a many-to-many relationship, or could also have a one-to-many relationship with B, or with A. So this is why I encourage, when you're looking at entity relationship sets, to think about it as two sentences, or one complete sentence for each entity, the way that this entity relates to other entities through that relationship. Okay, so I won't go over again the quote-unquote vocabulary. Okay. So that's what ER diagrams do. They define collections of data and their relationships to one another via these different kinds of relationships. Now, that's sort of an intermediary step that makes it easier to figure out how to then design the relations. Relations here can be thought of as tables. And when different tables have a relationship with each other, you can capture that via another table, which is the case here. We have an entity employees, an entity departments, and a relationship between them, works in. There's no constraints placed on the types of relationships or the types of connections between these sets. And so we can capture that with three relations. One relation for employee, one relation for department, and then another relation to connect the two. These are connected using unique identifiers called keys. Every relation will have a key. The key should be unique. So for any relation, the key, or the primary key, as it's sometimes called, must be unique. Those are the black underlined things here. So the department ID has a primary key, DID. That means that in that DID column, no number can appear more than once. There's another kind of key that I have here as a purple arrow. That's called a foreign key. A foreign key is a key that references the primary key of another table. The point of this is that any number, let's look at the DID column in the works in table, that any number that appears here in this column must also appear in the department table that this foreign key is pointing to. So I could not add in the works in table an entry like this. This entry would be invalid because this 7, which is a foreign key, does not appear in this list. Okay, so that's what the foreign keys do. Okay. Now, when you have unconstrained relationshiits, the way that you can capture this as a relation, or with relations, is to take the relationship, the works in, and make its own relation with a composite key. The composite key is here, the social security number and the department ID. And a composite key means that it's the composite of all of these keys together. It's the union, it's after you glue all of them together that the glued together thing must be unique. So here, like in the first two rows of this table, although 1, 1 appears 2 times, that's okay because the department ID is different. Okay. Then we talked about how to capture a different type of constraint. This is a participation constraint. These are called in ER diagrams, the participation constraints. And this participation constraint says that a department can have at most 1 employee. We can capture that participation constraint in relations using key constraints. If you're clever about the relations that you create and the key that you're using, then a keyed constraint in relations can realize a participation constraint in ER diagrams. Here, there's 2 ways that we can capture this. As opposed to having a composite key, like before, we can make the works in relation have only 1 column for the key. In this case, the department ID. And because the department ID is being used as a primary key, it cannot show up more than once in that relation. And that captures the participation constraint of a department only being able to have at most 1 employee. So this is one way of doing it, where you can create 3 relations. There's another way that you could do it with just 2 relations if you combine the department and the works in table. In fact, I'm going to rename this to emphasize that. So now we have 2 tables, and we've merged the department and the works in table. It makes sense, if we're going to be merging tables in this way, to merge the works in with the department, because in method 1, we chose the department as the primary key. And the department table also is choosing the department ID as the primary key. So we can just have the department table hold double duty and have that 1 primary key applied to the entire table. And then we have to add fields to it to capture the relationship. In this case, social security number and the CINS.
Professor, I have a question or 2.
Yes.
So just to clarify, for the methods 1 and 2, in method 1, department in works in table, that's the foreign key, right? But then in method 2, the SSN is the foreign key. Would that be correct?
Yes, that's correct.
Okay.
Except I should add to it that in the works in table, not only is the department a foreign key, it is also the primary key. So it's a primary key and a foreign key.
Is SSN also a foreign key in method 1?
Yes.
Okay, great. And so if SSN and department were a composite key in method 1, that wouldn't change anything. They would still both be foreign keys.
That's correct.
Great. Okay, thank you, Professor.
Yeah. Yeah, so up here, this is a composite key, and they're also foreign keys. So here, the primary key is the concatenation of SSN and DID. So, and when we get to the SQL language, we'll revisit all of these things with what's the SQL command to create these tables. But in SQL, you'll define you'll define a primary key. And in this case, it would be, for example, SSN DID. Let me make that bigger because I know it's very small. So I'll make it a little bit bigger still. Yeah, in SQL, when you're defining a table, you define what the primary key should be. And in that case, it will be defined in this way. So this is how you would capture a composite key in SQL. Actually, I'll copy that down. Where here, the works in table, this would have the primary key just being the department ID, right? This just has the one. Oh, very good. Okay, yeah. So here's another type of relation that you can do with key constraints, which is a one-to-one. So every member of A is connected to a member of B, and every member of B is connected to a member of A. You can do that with three relations, but you can actually capture it with just a single relation. Because here every A will be matched with some B, and every B will be matched with some A. And if you think about this, the size of A has to be equal to the size of B. So you'll never have more A's than B's or more B's than A's. In this case, A's and B's will have exactly the same number, and therefore you can just store them in the same table. And this is the way that you would capture this in SQL. So for the composite key from above, remember that was like this. The social security number and the department ID both inside of the primary key. That's how composite keys are captured. Here, though, we have essentially two primary keys. But in SQL, they only have the primary key. You can only use that word once, but you can use another keyword unique, and it behaves exactly the same way. So one has to be primary, one has to be unique. It doesn't matter which one's which because they're the same thing. And yeah, so this is the difference in SQL between having two primary keys and a composite key. We'll come back to that in like a month when we actually start getting into SQL. Why is this being so annoying? Okay. Oh, was I cutting out? Okay, can everybody hear me okay? I don't know, I'm checking with everybody else too. Okay, great. All right, well then I'll go on. So this is the last thing that we are talking about with ER diagrams. And this is something called a weak entity. So a weak entity is, let me actually write this. A weak entity is when one entity's existence relies solely on another entity. Okay, so one example that captures this is the idea of employees having an insurance policy with dependents. In America right now, most people get their health care through their employer. But besides an employer offering health care to the person who's employed, that healthcare policy can also cover their immediate family, wife, husband, children, and that's it. So for me, for example, I'm employed at Rutgers. I have a health insurance policy through Rutgers. My wife is also on my health insurance policy as a dependent. So my wife's name is somewhere on a Rutgers database for who's covered by health insurance policies by Rutgers. Now, other than being married to an employee, my wife has no association with Rutgers. So her sole reason for existing is through her link to me. And if I were to leave Rutgers, then I would lose my insurance through Rutgers, but my wife would also lose her insurance, because right now her insurance is, she's a dependent on my policy. So that's what a weak entity is. In this case, a person unaffiliated with Rutgers can only be as a dependent in a health insurance policy through Rutgers if they are connected to an employee of Rutgers. That's the only reason why that would exist in the Rutgers system. In addition to that, if that type of relationship exists and the employee leaves, then the dependent must also be deleted. So a dependent cannot stay without a connection to a currently employed employee. All right? So that's the scenario of what weak entities are. The way that this is captured in an ER diagram is that the relationship diamond is bold, and the weak entity rectangle is also bold. In addition to this, the key for the weak entity has a dotted underline. And that's to show that it cannot be used as a primary key. It can only be used as a composite key. Okay, so that's the way that this key will be showing up, is as a part of a composite key. So let's see how that would look here. So here's me. I'm an employee at Rutgers. I have a social security number and a name. That's the employee's entity. Nothing special about that. But these two tables are going to be the same table. Well, they can always be the same table. I suppose you could always split up tables, but you can always make it one table, where it's going to have one foreign key, which is the key of the, I'll call it the strong entity, although I'm just making that up. There is no strong entity, but the foreign key will be referencing the primary key of the other relationship. And then the key for the weak entity is going to be made a composite key with that. The reason why it's always a composite key is because the social security number should be unique. You could not have one dependent covered by two different employees. Like, let's say a husband and a wife both work at Rutgers. Then their child could not be a dependent on two insurance policies. If, for whatever reason, this couple decided not to have one insurance policy, but they want two, and I suppose you could do that. If they have a child, that child can only go on one of their policies as a dependent. So, yeah. But it could also be the case that a dependent could have the same name. So here's me and my wife in the policy dependent table. Here it's the combination of my social security number and her name. And maybe there's another employee with a different social security number, but they have a child or a wife with also the same name as my wife. Well, then that should still be a valid entry. And so that works with a composite key. The social security number part of it makes sure that no dependent can be on more than one policy. and the key name part of it is a composite key, so that way that's the way that a dependent and the person with whom's policy they're on are connected. They're connected via this key. Yeah, and then there's two other things. This social security number here, it cannot be null. You cannot have a null here and then, I don't know, John. This entry is not allowed because in weak entities, every, in this case, John would be a dependent. He cannot be associated with a null employee. Like a weak entity has to be associated with some existing entity to which it's related. So there's that condition as well that I've highlighted in green. The primary key, this foreign key cannot be null in this table. There's also something called cascading when you delete. So a cascade, it's like dominoes, right? If you knock one over, all of the others cascade and everything falls. So one thing starts and then it has that effect through multiple layers. In this case, if you delete an employee from the employee table, like if I leave Rutgers, then anybody who was associated with me must also be deleted. So in this case, that's my wife. That delete has to cascade to her as well. So if an employee leaves the company, not only do they lose their insurance policy, but their dependents also do. So that's it. Okay. Ooh. Any questions? None? Okay.
Are we supposed to circle social security number in this instance?
No.
Okay.
Yeah. Sorry. Yeah. Okay. Oh, and this I left as an exercise for you guys. I think this would make a good question. What is something that you can do with ER diagrams that you cannot do in relations? And this is the example. You cannot have this at least one relationship. It's fine in an ER diagram. I mean, it follows the what's allowable inside ER diagrams, but you just won't be able to capture this as relations. Yeah, I'd like to leave that as an exercise to you. So, okay, so that's it for ER diagrams. If there's no questions, we can move on to set theory, basically. Okay. Start a new page then. Okay, so this is called relational algebra that we're getting into. And today, basically, I think I'll just be able to go over essentially the vocabulary of it. Because I also have to spend some time talking about set theory. So I've already talked about relations that can be thought of as tables. So this is a table or a relation. And there's, names to these columns. Those are the attributes. One of them or many of them, there's going to be some key, whatever. But for the purposes of what we'll be going into, for relational algebra. So this is where the relation in relational algebra comes from, is it's about relations. And this can have some number of rows. And each of these rows, no matter what's the key, every row is going to be different somewhere than some other row. Okay, you're not going to have exactly the same copy of one row 2 times. No matter what key you choose, you have that guarantee. For any choice of key, every row is going to be unique from every other row somewhere. So now I'm going to be drawing a few more pictures for sets. So a set is a collection of objects or elements. And I'll capture that by drawing dots. So each dot here, this is an element of the set. Okay, so this set has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 elements. 12 elements. So the size of the set is 12. Okay? Now, elements of a set can be anything you want. Okay? Each element of a set can be anything. It can be numbers, it can be letters, it can be sentences, it can be video, it can be people, it can be abstract objects, it can be smiley faces, whatever. In the general notion of sets, it's just a collection of objects. Okay? So when I'm drawing a dot, that can represent a lot of different things. In this case, each dot is going to represent one row. So for example, this whole row, I'm going to be representing with, let's say, that dot. Okay? In this case, it'll probably be text of some kind. Text, numbers, whatever, because that's generally what's stored in rows. But in general, the elements of a set can be anything you want. So although I'm just drawing a dot, this dot is an element of a relation. In this case, it would be some row of a table. All right. Very good. Okay. So that's my interest. So this is the way that let me say something else quickly about this. So right now I'm just trying to put these things in context to know where we're going, why are we talking about sets, and all this type of stuff. So we'll have different relations, and let's say here, I don't know, I'll call this T1. And then over here, I'll have a different T2. And this has, I don't know, A, B. And this will also have some rows. Okay, each row in this, each row in this relation is also going to be unique in that relation. And it could be the case that if these two tables are related somehow, that, I don't know, maybe here's the name John. And then here is also the name John. Okay? And now that's the key in both of these relations. Here on T2, column A is the key, and here there's the name John. For T1, the primary key is C, and that is also a name John. So in this way, this T2 is also a set. Actually, let me do it this way. Let's say that this is the set for T2. Here's the set for T1. And then the black is in the set for T2. In this case, at least this entry, right, this green one with John, is pointing to a member that overlaps, or that there's an intersection between these two sets. Okay, so this is why we're talking about, and maybe we want to return all values where these two tables overlap, in which case if we were to return from the database of 12 things, maybe we only care about this intersection. And T2 will also have maybe some other elements. And then if we only care about this intersection, then we want to return, all of those results. And that's what we're doing in relational algebra. Okay, so we're talking about sets, but these sets correspond to relations. And then the algebra, part of relational algebra, is putting together queries. Basically set intersections, the unions between sets, projections, stuff. Okay, but just so you kind of know why we're talking about sets and what relational algebra, like what's the point of it. Okay, and this process of having many sets and returning some elements of those sets, that's called a query. And that's what we do with relational databases, is we're mainly interested in querying and searching through the data. So relational algebra is a way that, given many different sets, how do you phrase the query such that you get back the elements that you want? So in this case, how would I get back, this region? How would I state a query so that those elements are returned to me? Okay.
All right, Professor.
Yes.
Quick clarification. This would be two different sets then, right? Not just one big set, because T2 is referencing a set that intersects with the set in blue.
Yep.
Okay, so the set in black then, that's just that could be any size, right?
That could be any size.
Okay, great, thank you.
Yeah. So for example, here, the intersection between the two, each of these elements are going to be some unique name. Okay, I can call this green one that I've circled, I could call that John, which means that John appears in T1. Because T1 has 12 elements, this would have 12 rows. So it'd have 12 rows. Let's say that T2 is of size 4. So T2 only has 4 rows. And in this case, I don't know, John, Peter, Paul. Let's call this one Peter, Paul. That one's John. And so this would also have a Peter and a Paul. But here's a Susie. This is Susie. And Susie does not appear here. It's a name that doesn't appear in that column of T1. So that in that sense, they're not identical sets. Yeah. All right. I am going to turn off my camera. And very good. So I'm going to begin talking about sets. And just so we have a common notation and a common language that we can use when we're talking about sets. Okay. I will represent sets. One way I'll represent them is with circles. And this I will refer to as the world. Okay, the world is all of the elements of any set. So any sets that we have, maybe here's a set A, and here's a set B. They overlap a little bit, but they also have places where they don't overlap. Okay, and the world includes everything. So any sets are in the world somewhere. And the world we represent with this, omega. So that's a capital Greek letter O, omega. So for example, maybe one set is social security numbers. Another set could be the set of all integers. Okay, so sets can be infinite in size. Okay, you can still draw them as a finite circle, but some sets are infinite, like the set of integers is infinite. It could be, dates from, I don't know, 1/1/20 to 2/24/20. I mean, again, sets can be anything. Here, A could be social security numbers of people in New Jersey. And B could be social security numbers of people under 20. Okay, so here there's some people who are under 20 who aren't in New Jersey. Here are people who are in New Jersey but are older than 20. And then here is the set of people who are under 20 and in New Jersey. All right. Let's see, notation. Okay, I'm going to define a world. And in this world, there's going to be John, Paul, and Mary. Okay. These squiggly lines, curly brackets, are used for sets. Okay, so this is saying this is a set with three things, with three elements. Elements are separated by a comma. Okay, I could make a set A, John, and Paul. Okay, that's a different set. Here, A is a subset of omega. Is a subset of. Okay, so what this means is if this is omega, A is inside of omega, the subset. Also, A is in omega here. This is a proper subset of a proper or a strict subset of omega. So this is, here. If I had a B with John, Paul, and Mary, then B is a subset of omega, but B is not strictly a subset. That is, so this is saying basically less than or equal to. That's a C, by the way. It's a C, or it looks like a C. Okay, I'm not being sloppy with that. This here, let me try to make it very clean, just to emphasize that. I'm not being sloppy. Okay. So here, yeah, think of this as less than, and this is less than equal to. So B is less than or equal to omega. In this case, it's equal, but it is not strictly less than, like A is. A has fewer elements than omega. Oh, I said it's here. The size of omega is 3. So using these two lines here, that represents size. Okay. I think, do we need to talk about independence? No, we don't, thank God. Okay. Disjoint. Disjoint is when two sets, A and B, have no common elements. And here, sometimes I'll write the world as a rectangle. Sorry if I'm not always consistent. Sometimes I'll write the world as a rectangle, sometimes as a circle. So here, disjoint means that A and B share no elements. There's the complement. So here, if this is the world, and here's A, then the complement of A is written like A with a bar on top of it. And that are all of the elements not in A. It's called the complement of A. All right, so just for fun, let me pick out on somebody. So here's a set A and a set B, and I want to know, is A subset of B? How about Nicole?
Hey, Professor.
Hey.
I think in this case, A isn't a subset of B because there is a value that's not contained in B that's in A.
Very
Like,
good.
Okay.
Yeah, that's right. Yeah, very good. So here, A, answer. No. 3 is in A, but 3 is not in B. So yeah, you stated it correctly. I'm introducing some more notation. This is an element of, and this is not an element of. Right. So just as you say, A is not a subset of B because A has the number 3, and 3 does not appear in B. So very good. Okay. Okay. Now, there's in relational algebra, there are 7 operations. The first one is a union. That's written like this. That means union. Okay. And the union is a set where is a set such that I'll have to write this down in English afterwards. X in A or X in B. And in this notation, writing it this way, this would be, it can be read as like for all X or all X. So A union B are all things such that X is in A or X is in B. And so this would look, if that's A and that's B, it includes things that are in A or in B. Okay, that's the union. Okay, so I don't want to throw a bunch of like weird notation at you, but it will make things simpler later. All right. A intersect B. So again, it's a set X such that X is in A and X is in B. Okay. That's the intersection. Oh, union. 2. Intersection. Okay. By the way, I'm introducing this type of notation to you because I don't think it's that complicated. Although I'm sure it's new to many of you, it's not that complicated, and it can make your job a little bit easier when you're writing things down. That being said, this is not a formal math class, and so if you want to be more verbose, then that's fine. I don't require you to use this type of notation. Okay. There's also a set difference. So and this is used, the minus symbol here means set difference. And so this are those elements x such that x is in B and not x in A. That would be these elements. I really should have a bigger screen. Minimize that. Okay, that helps a bit. Okay. Now, you know what? I'm going to try to shrink this down a little bit. I don't want things to be too busy, but I also want to. So. Sorry, this is an attempt to actually make my notes cleaner. Let's see how it works. There we go. And make that smaller.
Also, Professor?
Yep.
Is not x an element of A? Is that the same thing as saying like x with the element and symbol and with a slash through it? Is that the same?
Yes. Yeah. So you could say x in B and x not in A. Yep.
Great.
Yeah.
Thank you.
Mm-hmm. Yeah. Yeah. Very good. Mm-hmm. Okay. Sorry, I don't know if you know, I might post some of my notes as a PDF sometimes, or at some time. And if I do, there's a very strict width requirement that is this width on the screen right now. So if I don't fit everything in that width, then things won't print off nicely. All right, now there is a commonality among these three, and that is that they work on the same kind of tuple, i.e. the same schema. Okay, so now I have to teach another word, tuple. A tuple are just the names of all of the columns. That is called a tuple. So here, if you have a relation, and here's some columns, this here the collection of that is called a tuple. Okay, so that is to say, if we have a table A with columns A, B, and C, and another table B with columns A, B, and C, then we can union these together, we can intersect these two, and we can take their set difference. But if B had, let's say, maybe another column D, then we can't take the union of A and B. A union B with this A and this B won't work. Because, I mean, would we take these elements and put them here? That would be one way of doing it. If A and B looked like this, then A union B, you can just take, this region of A, all those rows, paste it to B, and then that would be the set A union B, right? All of the columns of A and all of the columns of B together. But if B has a different, has an extra column, for example, then there's no way to do this. So these all work on the same tuple. That's what I mean by that. I'll draw a little diagram here, just, I don't know, like if here's A and here's B, then A union B just be this, A and B, right? So if they're the same tuple, you can concatenate the tables vertically. That's also the same schema. Okay. So I don't want that to go off the same schema. Okay. So now this is a slightly different class. The first one is the cross product. Okay, this is A times B. Actually, yeah, it's sort of, well, okay. How do I say this? Okay, I'll do an example. I think that'll be the easiest way to show this. So let's say if we have a set A that is John, Paul, and Mary, and a set B that's John and Paul. Cross product, this is all possible pairings. So here, if we want to take the cross product of A and B, well, all possible pairings means you take, for example, the first element and pair it with all of the elements it can be paired with. So we'd have John and John. This here, this is called a tuple, aka a vector. I apologize if I go back and forth if I talk about tuples sometimes and vectors other times, or this kind of thing. Yeah, I'll do my best to not confuse you. But you will hear both of these things commonly. Okay. Oh, and now this, I want to emphasize, this is one element. Remember, elements are separated by a comma in sets. So this is one element, where that element is a tuple. Okay, and then we also have, John paired with Paul. So that's also in this set. Moving down the line, well, let's see, I'll keep those. So John, Paul. Paul can also be paired with John and Paul. So then this set would also include Paul and John, and Paul and Paul. Okay. And finally, Mary can be paired two different ways. So this would also include Mary and John, and Mary and Paul. And that's it. That's the size of the set. Okay, so there's 6 elements. Yeah. Why is there 2 Pauls in A? Do we need to repeat Paul, 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 John again? What if there are 2 Pauls in A? Very good question. I was just thinking that I would bring this up. Yeah, so I'll put this up here as sort of a note about sets. Actually, I'll put it here. Note. Okay. A set doesn't have any repeats. That is, if you have A equal to 1, 2, 3, 3. No, I won't use 3. 1, 2, 6, 7, 6. Right? Now 6 is appearing 2 times. This is the same as 1, 2, 6, 7. Okay, so there's no need to repeat things in the set. Also, order doesn't matter. So 1, 2, 6, 7 is the same thing as 7, 2, 6, 1. Okay, so order doesn't matter in a set. It can just be thought of as a bag with balls in it. And it doesn't matter how the balls are organized. If you shake up the bag, the balls might change their order, but it's all the same stuff inside of the bag. So,
Professor, for the cross products that you're doing, then would John and Paul and John be the same thing then? Would you have to write them twice, or
would John and Paul and John be the same thing? Let's see. So for tuples, order does not matter either. Let me answer that a different way. Like algebraic multiplication, 2 times 5 should equal 5 times 2, right, in algebra. It shouldn't matter which one goes first. It's the same operation. So similarly, we want this property to also apply to cross products. The way that this would work in cross products is, if you wanted to, think about this, this could be 2 plus 2 plus 2 plus 2 plus 2. Or you could have 5 plus 5. Okay. Let's call this way taking the first element and pairing it. So that's what we've done here with the green, or with the red, matching John, taking the first element of A and pairing it up with all elements of B, then choosing the next element of A, pairing that with all elements of B, and then choosing the next one of A and pairing it with all elements of B. Now, it shouldn't matter. Let's say that that's this way. Then this way would be pairing B with A. And at the expense of making this really messy, I could do this. This would be another fine pairing. Actually, I'll erase this. Okay. Another way I could pair this is this way. I could start with an element of B, and I could pair that with all of A. So if I do that, then my set looks like John, Paul, John, Mary. And now I can do Paul. I can match Paul, the next element of B with all of them of A, in which case I'd get Paul, John, Paul, and Paul, Mary. Now, the question is, are these two equal? And they should be. They should be equal. So here we can see that there's a John, here's John, Paul, here's Paul, John, here's Paul, Paul. Wait, what am I missing? Sorry, Paul, Mary, John. Right. So Mary, John here is the same as this. Okay, so it doesn't matter in the tuple, the order either, because we want each of these to also be equal. And the same thing here, Mary and Paul, Paul and Mary, those are also the same. So it doesn't matter which order you put things in. For the pairing, it's like multiplication. I mean, if you pair 2 and 5, it's the same thing as pairing 5 and 2. They're a pair.
Just sorry, my audio is weird. When you do the cross product, you want us to like 6, like completely, like John, Paul, Paul, John, Paul, Mary, Paul.
As opposed to what?
As opposed to like not having the. I'm still a little confused if John, Paul, and Paul, John are the same within this set. But technically, if you said order doesn't matter, then you're just having the same thing, and you said that there shouldn't be repeats.
What would be the repeat here? Okay, let me start fresh. So a set A and a set B. What do you want the set A to be?
Set A was John, Paul, and Mary.
Yep.
And then
Okay.
set B was John, Paul, same as before.
Okay, same as before. Okay, and I won't write it. Okay.
I'm asking like for when you do the cross product, when you multiply John by John and then John by Paul, but then you also multiply Paul by John, is that the same? Like, do you want us to like always include like all like that extra element, even if it's the same thing?
Oh, are you saying, for example, here's Paul, John, and here's John, Paul. Are those the same thing? Here
Yes.
they're not. Yes, right. Here, these are two different pairs. Each pair is valid, but okay. Yeah, so long you do every possible pairing. Yeah. Sometimes that, it's legal that you can have these being the same thing while at the same time having these be different. It is that way. Actually, that's the first time I'm kind of noticing this, but yes, this is true. The ones in black are the same, and the ones in purple are different. The reason why the black ones are the same is because there was a procedure that was gone through to produce all the pairs. And the number of pairs that you produce are going to be the number 6. And for every pair, there's going to be a one-to-one matching between them. The reason why this is again, for the property that A times B should equal B times A. So here's B times A, and here's A times B. So you can multiply things in whatever order you want. Yeah, but I notice now that could be confusing. If you go through a few cross-product examples, it might become more comfortable why that's the case. It should be 3 or 6. If there were a question on how many sets or how many orders in the cross product in that situation, the answer would be 3 or 6. Okay. This is a good question. And I'm going to try to use this sort of notation. What is the size of A times B? The size of the set A times B is equal to the size of A times the size of B. So here, with A, the size of A is 3, the size of B is 2. Therefore, the size of the set A times B is going to be 3 times 2, or 6. Anthony, does that answer your question?
Yeah, that's it. Thank you.
Okay, yeah. All right. Here's one question. Here is another question. All right. Here's one question. Here's another question. Or no, here's yeah. Okay. So let's say we have A is the set 1, 2, 3. B is the set 3, 4. Question. Is A subset of A times B? Okay. I'd like one of you guys to answer this. You can take a minute to think about it. If somebody thinks that they have an answer, they can type it or unmute themselves. Otherwise, after a minute, I'll call on somebody randomly. boy. Okay, sorry guys. I'm just now noticing that I heard people logging out. So yeah, class is over. I'll note that as an exercise for you, and we'll pick it up here next class. So have a good weekend.